So in the last section, we were discussing about solving this question using the concept of laws of motion and equations of motion. And now we'll solve this question using work energy theorem. So what is work energy theorem? What does it states? Work energy theorem states that the work done by all the forces, where the forces, which forces, all those forces which are acting on the block, is equal to change in kinetic energy of the block. Now see, while we calculate this question, we need to address something very critical here, because this much portion which is BC, which we assume AC to be x, right? We assume this much length to be x and BC to be 2x. AC here is rough, whereas BC is smooth. So what I've done is, for the ease of calculation, for the clarity in understanding, what I have done is I have chosen work done by all the forces on the block into two halves. I split it into two halves. One, work done along BC plus work done along CA. See, if you try to do it, in a very clear way, you can actually split it up. Work done by BC, you can find out the change in kinetic energy there, and then you can separate it as work done by CA and find out the kinetic energy in work done along CA, and then you can add those two terms. That's up to you. You can do that, but I think it will be really time consuming here, so I'm gonna skip that part. I just go directly into the LHS. Okay, so if you apply work energy theorem for this part BC, the block is kept at BC. Let's say this is B and this is C. Along this path, along this complete path, the friction is zero, and the body here is sliding downwards, right? So what are the various forces acting on it? Normal reaction perpendicular to the inclined plane, mg sine theta horizontal to the inclined plane, mg cos theta perpendicular to the inclined plane in the opposite direction. Now how did we arrive at this? Because we know that weight acting downwards can be resolved into two components, which is horizontal component like this and the vertical component like this, right? Now what is work done by a vector f? This is equal to okay, let me just write it down one time. This is equal to vector f dot vector s, which is further equal to magnitude of vector f times magnitude of vector s times cos of the angle between them. Okay, not the theta we are talking here, it's the angle between the force and the displacement. So in terms of mg sine theta, mg sine theta is acting like this, right? Okay, wait, maybe I'll go to the specific slide. Yeah, okay. So while you calculate mg sine theta is acting like this. This is the direction of mg sine theta, and the displacement is also in the same direction, which means angle between them, theta, is equal to 0 degree here. So instead of cos theta, I can replace this as cos 0 degree, which is equal to 1. Therefore, what is W done by mg sine theta? It will be force into displacement, which is mg into sine theta, which is 2x into mg sine theta. So we discussed W mg sine theta. Now let us find out work done by the normal reaction. So what is work done by the normal reaction? When you calculate work done by the normal reaction, what do? Same equation, work done by normal reaction will be equal to magnitude of normal reaction into displacement, which is 2x, into the angle between normal reaction, okay, maybe like this, angle between the normal reaction and angle between the displacement. What is the angle between these two? The angle between them is theta is equal to 90 degrees, in which case instead of cos theta here, what can I write? I can write here 90 degree. What can I write? I can write here 90 degree. So what is cos 90? Cos 90 is 0. Therefore this becomes times 0, and work done by normal reaction is therefore equal to 0, right? which means we have calculated work done by mg sine theta, and we have calculated work done by normal reaction, which is actually equal to 0. Now we have to calculate work done by mg cos theta. Now one more time, what is work done by one force is equal to? It is equal to magnitude of that force into displacement produced by it into cos theta, which is the angle between force and the displacement. What is the force that is considered here? The force under consideration here is mg cos theta acting downwards. What's the direction of displacement? Direction of displacement is like this. And what is the angle between them? The angle between them is theta is equal to 90 degree. Therefore, what would be cos theta here? Cos theta here would be equal to cos 90 degree, and therefore W by mg cos theta will be equal to mg cos theta and 2x into 0, and therefore work done by mg cos theta is also equal to 0, which means we evaluated this part as well, which is equal to 0, right? Now we have found out work done along BC, wherein normal reaction and mg cos theta component do not contribute. The only force contributing here is mg sin theta. Are we done with the question? No, because we have to find out the work done along the path CA. Now let us see what happens along CA. See, along CA, what are the various forces acting on the block? There are 4 forces acting on the block: normal reaction, mg cos theta, mg sin theta, and Fk. Now we can directly from the previous discussion say that work done by mg cos theta will be equal to 0, work done by normal reaction will be equal to 0, and all we are supposed to find out here is work done by mg sin theta and work done by friction, right? Let's see how. So we can say that work done by mg cos theta is 0, and work done by normal. Okay, I think it's better we calculate all the values here. So what is work done by mg sin theta? Mg sin theta is acting in this direction. What is the direction of displacement? Displacement is also acting in the same direction. What is the angle between them? Angle between them is theta is equal to 0 degree. So what is the value of cos theta? Cos theta the value is cos 0, which is equal to 1. Therefore, work done by mg sin theta will be equal to x into mg sin theta. Here it's not going to be 2x. Why? Because the displacement is from C to A and the measure of C to A is x. That's the difference which will come into picture. All right. Okay. Now moving on to the second work, which is done by mg cos theta. So mg cos theta is acting downwards like this, whereas the direction of displacement is inclined like this. The angle between them is 90 degree. So we have cos theta to be replaced by cos 90 degree. What is cos 90? 0. So this complete work done is 0. So mg sin theta we have found out. Work done by mg cos theta is equal to 0. Now let us see the case of normal reaction. Normal reaction is acting upwards like this. Direction of displacement is downwards like this. The angle between them is theta, which is equal to 90 degree. Therefore, work done by normal reaction will be n into x into cos 90. What is cos 90? It is 0. So work done by normal reaction is also equal to 0. So we have calculated mg sin theta, mg cos theta is 0, normal reaction is 0. All we need to find out is work done by friction. And what is work done by friction? So maybe I'll just erase out these things. Right? We don't need these to find. The work done by friction. Work done by friction is magnitude of friction into the displacement into the angle between friction and the displacement. Now let us see. Friction is displacement is downwards like this. Friction is opposing to it, right? Maybe one more time. Friction is acting like this. Displacement is acting like this. What is the angle between them? Angle between them is theta is equal to 180 degree. What is cos 180? Cos 180 is, instead of cos theta, we can write a cos 180. And what is the value of cos 180? Cos 180 is minus 1. So we can say this minus mu k into mg cos theta into displacement, which is x. And we can now say that it is mg cos theta and normal reaction don't appear here. Only two forces appear, which is mg sin theta and mg cos theta. And once we have this, okay, wait, is there a mistake here? Yeah, okay. So now if we apply work energy theorem, work done along BC plus work done along CA is equal to change in kinetic energy. Change in kinetic energy is half into m into VB square minus VA square. VA represents the velocity when the block was here. VB when the block was here. It is given to us as the body was earlier at rest, and finally also it is at rest, which means VB and VA are the same, which means VB square minus VA square is equal to 0. So it further means that work done along BC plus work done along CA will be equal to 0. What is work done along BC? We have found out work done along BC to be 2x into mg sin theta. So we have 2x into mg sin theta. What is work done along CA? We found out work done along CA to be, what was the value? Okay, now I'm getting a bit confused here with the writing here. Okay, right. So mg sin work done along CA is work done by mg sin theta plus work done by kinetic friction, which is equal to work done by mg sin theta is mg sin theta into x, by kinetic friction is minus mu mg cos theta into x. So now what we can do is 2 mg x sin theta plus mg sin theta would be equal to 3 mg sin theta. Maybe I've used the wrong brackets here. That's what's putting me in a confusion. Yeah, so now the bracket is correct. Yes, now the brackets are correct. All right. So we have 2 mgx plus mgx as 3 mgx sin theta into x. And then mu mg cos theta will be transposed to the RHS. So that it's mu mg cos theta into x. Now mg by mg is 1. X by x is 1. So we have 3 sin theta is equal to mu cos theta, which further gives us sin theta by cos theta is tan theta. So we have 3 tan theta is equal to mu. Therefore, mu k can be written as 3 tan theta. And if you compare this with the given question, what we have is the value of k is mu is equal to k tan theta.